A man is walking a riverbank in western Siberia, and he is not looking for a human being. He's looking for ivory. His name is Nikolai Peristov, and he carves mammoth tusk for a living, which in this part of the world is a real job. The Irtish eats its own banks every spring. Ice Age Siberia is buried in those banks, and every year the river cuts a little deeper and hands another few thousand years of it back. In 2008, on the left bank north of a village called Ust-Ishim, he picks up a piece of bone eroding out of the sand. It's the shaft of a thigh bone, no skull with it. No tools, no hearth, no grave, no site at all. The river has already taken all of that, if it ever existed. Just the bone. He doesn't know what it is. 2 years later, an anatomist looks at it and says something that changes everything. This is human. What comes out of that femur over the next 4 years is one of the strangest objects in all of science. Not a skeleton. Not a burial, not a culture, a clock, a single leg bone from a man who died about 45,000 years ago, carrying inside it a measurement that no pile of stone tools on Earth can give you, the date of the moment our species and the Neanderthals mixed. Not a guess at that date, not a model of it, a measurement read directly off the length of the pieces. This is the story of how one bone with no sight, no skull, and no name became the most precise timekeeper in human prehistory. Call him Vesh. That's a name we're inventing because he doesn't have one and never will. Everything else about him comes out of the bone, and the bone turns out to be talkative. He's male. We know that from the genome, and we know it twice over from the shape of the shaft. The upper end carries a heavy ridge where the big muscles of the hip anchor, and the middle of the shaft is a teardrop in cross-section rather than a rounded pillar. That teardrop is a walker's bone. It's the pattern you see in early modern humans, and it's not the pattern you see in Neanderthals, whose thigh bones are rounder and thicker-walled. Before anyone reads a single letter of his DNA, the shape of the bone has already said, "This is one of us." Then there's what he ate. Carbon and nitrogen locked into the protein of his bones say his diet came from land plants and the animals that grazed them, and also, in a serious way, from the water. Freshwater fish, most likely. That same signal shows up in other early Upper Paleolithic people in Europe, and it matters more than it sounds. A group that can pull food out of a river is not fully at the mercy of the herds. It's a way of living at high latitude that doesn't depend on being lucky with mammoth, and he's living far north. Ust-Ishim sits at about 58 degrees north, up level with Juneau, Alaska, or the top of Scotland. 45,000 years ago, this is open, cold, wind-scoured country. There are still Neanderthals alive somewhere to the south and west of him at this point. Nobody has painted Lascaux yet. Nobody will for another 28,000 years. He's living during a warm swing inside the Ice Age, one of those short interstadials when the cold eases for a few centuries and the country opens up. The predators up here are serious. Cave lion, wolf, and a winter that kills more people than either. Now the date. This is where the bone starts being a scientific instrument instead of an artifact. 2 separate samples were cut from it, about 900 milligrams the first time, 450 the second, and dated at Oxford years apart. Both came back at 41,400 radiocarbon years, one with an error of 1,300 years and one with 1,400. Two independent runs, same answer. Convert those radiocarbon years into real calendar years, and the bone lands between about 43,200 and 46,900 years ago at 95% confidence. So, about 45,000 years old, give or take a couple of thousand. That range is the honest number, and it's worth holding onto because everything downstream inherits it. That date alone made him famous. He is the oldest directly radiocarbon-dated modern human ever found outside Africa and the Middle East. Not dated by the layer he was in, there is no layer. Dated by his own bone, his own collagen, his own carbon. And here's the thing that should feel strange. We have no idea what tools he made. We don't know what he believed, who buried him, or whether anyone did. Archaeologically, he is almost nothing. A stray find with no context, the kind of thing that would normally sit in a drawer forever. And he is about to settle an argument that 1,000 stone tools couldn't. To understand what they pulled out of him, you need to understand what a genome is, not the poster version, the physical version. Inside almost every cell of your body, there's a set of instructions written in a 4-letter alphabet, about 3 billion letters long. That's the genome, but it isn't one continuous scroll. It's split into 46 separate pieces called chromosomes, and those come in pairs, 23 from your mother, 23 from your father. 2 copies of nearly every instruction sitting side by side. That pairing is the whole trick, and it's about to become a clock. Because here's the part most people never get told. When your body makes an egg or a sperm cell, it does not simply hand over one chromosome from each pair. Before the split, the 2 chromosomes in a pair line up against each other, break at matching points, and physically trade sections. The chromosome that gets passed on is a mosaic, a stretch from your mother, then a stretch from your father, then back again. That shuffling is called recombination, and it happens every single generation without fail in every sexually reproducing thing on the planet. It happens a specific number of times. That's the crucial detail. Each chromosome gets cut and spliced only a small number of times per generation, roughly 1 to 3 crossovers on a typical chromosome, not hundreds. So a block of DNA inherited whole from one ancestor doesn't vanish in one step. It gets shortened, chopped a little on each pass, generation after generation. Now hold that thought and go back to the bone. Ancient DNA survives best in the hardest, densest bone, and a thigh shaft is about as dense as a human gets. 9 samples were taken from it, between 41 and 130 milligrams each, pinches of powder. Most of what comes out of a bone that old is not the person. It's bacteria, soil, fungus, everything that has moved through the ground for 45,000 years. In these samples, the fraction of DNA fragments that were actually human ran from under 2% up to about 10%. Everything else is noise, and what survives isn't long, elegant strands, it's shrapnel. Ancient DNA breaks into pieces mostly shorter than the length of a tweet, and the chemistry decays in a specific way. One letter, cytosine, tends to rot into another at the ragged ends of each fragment. That damage pattern is a signature. It's how you tell 45,000-year-old DNA from a lab worker's sneeze, and it's why claims of ancient DNA before roughly the 1990s were mostly wrong. They cleaned the damage off enzymatically, threw out anything under about 35 letters, and read what was left over and over. The result is the thing that makes this bone extraordinary: 42-fold coverage of his autosomes. That means every position in his genome was read on average 42 separate times from 42 different fragments. That is not a sketch of a genome. That's better data than most living people have ever had taken from them. Contamination from modern humans came in under 1% of the fragments, so the record is clean. 45,000 years after he died, we have his instructions, near enough complete, in front of us. The question is what to ask them. Start with the thing everybody wants to know: how much Neanderthal is in him? The answer is 2.3% plus or minus 0.3%. That is startling for how unstartling it is. Living East Asians carry somewhere around 1.7 to 2.1%. Living Europeans about 1.6 to 1.8. A man who died 45,000 years ago in Siberia has essentially the same amount of Neanderthal ancestry as a person walking around Seoul or Madrid today. Slightly more, if anything. So the mixing wasn't a slow trickle that built up over the last 40,000 years. It was already finished before he was born. He also carries no detectable Denisovan ancestry at all. Living people in New Guinea and Australia carry a real slice of it, and mainland East Asians carry a trace. He carries none the tests can find. Whatever his ancestors did, they didn't do it with Denisovans. Now the part that turns him into an instrument. To find Neanderthal DNA in anybody, you look for positions where the Neanderthal genome carries one version of a letter. Sub-Saharan Africans uniformly carry the older version, and the person you're testing matches the Neanderthal. Africans are the control because their ancestors weren't part of this mixing. When a stretch of your genome keeps matching the Neanderthal in a run, that stretch came from a Neanderthal. Line up his chromosome 12 against the same chromosome in 15 living people, and you don't need statistics to see it. The living genomes are speckled Neanderthal ancestry scattered in short flecks like confetti. His is striped, long, continuous, unbroken blocks. That difference is the whole episode, because we know exactly what shortens those blocks: recombination. The chopping that happens every generation, at a rate we can measure directly in living families by comparing parents to children. So the logic runs backward and it's clean. A Neanderthal ancestor hands over whole chromosomes. Their child's chromosomes get cut and spliced, and the Neanderthal material comes out in long pieces. Their child's a little shorter, and so on down thousands of generations until in you it's confetti. Long blocks mean the mixing was recent. Short blocks mean it was long ago. The average length of the pieces is a stopwatch that started running the moment the two populations met. Measure his pieces against ours, and they come out roughly 1.8 to 4.2 times longer. Feed that into the recombination rate, and you get a number in generations, not years. Between 232 and 430 generations passed between the interbreeding and the day he died. That's the raw measurement. Everything after it is arithmetic. Multiply by a generation length of 29 years, the standard figure from studies of hunter-gatherer and farming societies, and you get roughly 7,000 to 13,000 years before he lived. Put that window on the calendar using his radiocarbon date, and it lands at about 50,000 to 60,000 years ago. Sit with how good that is. Before this bone, the best estimate for when Neanderthals and modern humans interbred was somewhere between 37,000 and 86,000 years ago. That's not a date, that's a shrug with error bars. One femur cut it down to a 10,000-year window. And here's why it carries weight that other kinds of dates don't. This method doesn't need to assume how fast DNA mutates. Most genetic dating does, and the mutation rate has been argued over for decades. Different methods have disagreed by a factor of 2, which is the difference between an out-of-Africa migration at 60,000 years and one at 120. Block length doesn't care. It runs on recombination, which we can watch happening in living families this year, in real pedigrees and count. It's closer to measuring the length of a shadow than to reading a theory. There's one more reason this only works on him and not on you. Think of recombination as a shredder that runs once per generation. Feed a document through it 200 times and the strips are still long enough to read a phrase off. Feed it through 2,000 times and you have dust. You can still prove the document was there. You can't measure much from the size of the fragments because they've all been ground down toward the same tiny scale. That's the difference between his genome and a living one. In us, Neanderthal ancestry has been through roughly 2,000 generations of shredding, and the flecks are so short that dating the event off them is guesswork with wide error bars. In him, it's been through a few hundred, and the blocks are still long enough to hold information about when the shredding started. The signal decays with time, and he's close enough to the event to still carry it. That's why a single well-preserved old bone beats 1 million modern genomes for this one question. Not because there's more DNA in it, because the DNA in it hasn't been cut up yet. That said, be honest about the soft spots because they're real. The calculation assumes the mixing happened as one clean event. It almost certainly didn't. The authors themselves noted that a handful of unusually long fragments in his genome hint at additional, later mixing that the single-event model smooths over. And the 29-year generation length is a choice. Use 25 instead and the whole window slides. The measurement in generations is solid. Turning generations into years is where the judgment lives. The block length date is the headline, but it's not the only clock in the bone. There's a second one, and it works on the opposite principle. Mutations accumulate at a slow, roughly steady pace. You are separated from him by about 45,000 years of them. His lineage stopped accumulating the day he died, so if you line his genome up against living genomes, his branch is short. Count the mutations he's missing, divide by the years the radiocarbon date says are missing, and you get the mutation rate itself directly without assuming it. That number came out at about 0.4 to 0.5 mutations per billion letters per year. In plain terms, roughly 1 to 2 new mutations have appeared per generation line per year across Eurasian populations since he was alive. They ran the same trick on his Y chromosome and got a faster rate, around 0.76 per billion per year, which fits what we know mutations pile up faster in males, because sperm production runs through far more cell divisions than eggs do. And they got a third rate for mitochondrial DNA off the radiocarbon date alone. Why that matters is easy to miss. The mutation rate is the exchange rate of human prehistory. Every genetic date, when we split from Neanderthals, when populations diverged, when anybody left anywhere, is priced in it. And for years there were two competing rates that disagreed by nearly a factor of 2. His bone came down firmly on the slower side, matching what geneticists measure directly in modern parent and child trios. The slower rate stretches everything: older splits, deeper divergences, a longer human story than the fast rate allowed. One femur out of a Siberian riverbank helped settle the units that everything else gets measured in. Then there's the question of who he was to us. The answer is genuinely strange. He shares slightly more with present-day East Asians than with present-day Europeans, but compare him to ancient Europeans instead, a 24,000-year-old boy from Malta in Siberia, an 8,000-year-old hunter from Spain, and the tilt disappears. He's equally related to all of them. That pattern means he sits at or just before the split between the western and eastern branches of Eurasia. He predates the divide. He's also not especially close to the Anj of the Andaman Islands, who have long been treated as the descendants of an early coastal migration around the rim of Asia. He's not on that branch either, which leaves the conclusion that makes him lonely. He belongs to a population that seems to have left no direct descendants, not in Siberia, not anywhere. His people got to 58 degrees north, lived there, fished there, and then ended. He's not our ancestor. He's our cousin from a wave that broke and drained away. And that is exactly what makes him useful. Because he isn't on anybody's family line, he can't be accused of special pleading. He's a fixed point, a dated, high-quality genome from a moment nobody else can reach, and the entire field now uses him as a calibration weight, hanging other ancient genomes off his date. Now the argument that gets loud. Every non-African alive today carries that same Neanderthal ancestry from the same mixing. Aboriginal Australians carry it too. If the mixing happened around 50 to 60,000 years ago, then the ancestors of every living non-African, Europeans, East Asians, Australians were still one population at that point. Nobody in that line had reached Australia yet, but at a rock shelter called Majidbeb in northern Australia, archaeologists date human occupation to around 65,000 years ago, using a method that measures how long buried sand grains have sat in the dark. Both of those can't be true about the same people. Either the Australian dates are wrong or the layers are mixed, or somebody genuinely got there 15,000 years early and left no genetic trace in living Australians whatsoever. The bone doesn't resolve that, it just refuses to let it be ignored. Science is supposed to revise itself, so here's the revision. 12 years on, his measurement has not been overturned. It's been sharpened by the same method applied to better bones. In 2024, 2 teams did to a handful of other early Europeans what was done to him. A skull from Zlady Kun in Czechia, a scatter of bone from a cave at Ronnies in Germany, around 45,000 years old, where the pieces turned out to belong to a small group of related people. Their Neanderthal blocks are longer still than his. Same logic applied again, longer pieces, less chopping, closer to the event. Those genomes put the shared mixing between about 45 and 49,000 years ago. A parallel study working from 6 ancient genomes put it as one extended period centered near 47,000 years ago, running from roughly 50,500 to 43,500. Notice what happened there. The window moved a little later than his 50 to 60,000 estimate, and it got tighter. That's not a refutation. That's the same clock being read with a better lens, and the 2 readings overlap. His answer from one bone with the tools of 2014 was already in the right neighborhood, but the newer dates make his life stranger, not simpler. If the mixing was centered around 47,000 years ago and he lived around 45,000, then he isn't a distant descendant of that event. He's practically standing in it. A few dozen generations, maybe. His Neanderthal great-great-grandparents are close enough back that if his people kept stories, the story would still have been told. And the squeeze on Australia gets worse, not better. Push the mixing later and you shorten the time available for anyone descended from it to cross Asia and reach the far side of the world. Somewhere between the mixing and 45,000 years ago, people covered the distance from the Middle East to Siberia and separately to the edge of Australia. The 65,000-year date at Majidbeb still sits out there, unexplained by any of it. That's not a scandal. That's what a live argument looks like, and the bone is why the argument has to be had with numbers instead of opinions. Step back and look at what actually happened here. A man carving mammoth ivory picks up a piece of bone off a riverbank. He isn't a scientist. He doesn't record the exact spot because he's collecting for his craft, not for a journal, which means we can't even say precisely where it came from. There's no site, no tools, no burial, no skull. By every traditional standard of archaeology, this find is close to worthless. And it turned out to hold a clock, not a metaphor for one. A physical mechanism running inside his cells while he was alive and frozen at the moment he died, chromosomes lining up, breaking, trading pieces, chopping ancestral blocks a little shorter every generation. Nobody designed it to be a clock. It just is one, and it can be read. That's the difference between a measurement and a story. 1,000 stone tools can tell you people were here, and roughly when the layer formed and what they were doing with their hands. They can't tell you that 8 to 13,000 years before this particular man drew breath, his ancestors and another kind of human had children together. Only the pieces can tell you that, and only because they're still long. He was one man on a cold river near the end of a line that went nowhere. He fished, he walked, he died young enough that his thigh bone stayed strong, and everything he knew was lost inside 100 years. The one thing he could not lose was the shuffling in his own cells, which had been quietly recording the date of an event he had no way of knowing occurred. 45